Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss about the velocity triangles and we'll derive the work done of Pelton wheel. So in our last lecture, we have already discussed about the working principle of Pelton wheel, and here we'll derive the work done of Pelton wheel and we'll draw the velocity triangles at inlet condition and outlet condition. So before discussing about this one, let me tell you how this turbine will work and how the impact of water will be on the blade. So actually, the velocity triangle will be drawn on the blade or bucket, you can say. Actually, this is the bucket which is fitted on the runner, and this is the top view part of a bucket, we can say, and this is the impact of jets on the bucket. So first let's try to understand where this bucket is fixed. So if you have seen our last lecture, there we can you have seen this is the runner. This is the runner part, and runner is the part of turbine, and all these buckets are fixed on the runner, and the buckets will be like, suppose the buckets, or we can say blades, or it can be also called as vanes also. So all these names are same. All these buckets and vanes or blades, what we can call, these all are fixed on the runner part. Yeah, and this bucket, or you can say like how it is, it looks like this actually, but I have drawn in the side one, that's why it's visible like this. And the impact of jets will, like, suppose this is the pipe is there, and from the pipe nozzle is fitted, and from this nozzle the water used to strike on this. Okay, and this pipe or penstock is attached to the dam, so that from the dam the water used to flows and it used to strike on the bucket. And the bucket is like, here you can see as this I have told you, this is the top view of this bucket. So this is the middle part of this bucket, or this is called actually splitter. This part actually called splitter. So the water used to strike on the splitter at this point. The water used to strike at the middle of this bucket, and that is called splitter. So once it strikes on this, so water will be started coming out from this. Like, you can say this is the inlet of this bucket, and when this water is strike to this one, there it will come out with the surface of this bucket, and it will come outside from here, from this point. Okay, so that the same diagram it was taken here, that this is, suppose, the impact of jet or impact of fluids on this bucket, and it used to strike on the splitter. So the splitter with the after that it used to go like this. It used to come out, the water used to come out from this bucket. It is like this. Okay, so this is for outlet, and this is also can consider as the outlet of the bucket. So here we'll derive the velocity triangles for this, and we'll derive the work done. We'll draw the velocity triangle and we'll derive the force and work done of the Pelton turbine. So this is all about what I told you, like how it is working. And the outlet triangle of this is actually already we have drawn the previous diagram, like previous topic what we have discussed, impact of jets. The impact of jets, when it is this is also called as the impact of jets. Number of blades are here, number of curved blades are fixed on a runner. Previously, if you have seen our previous lectures, that impact of jets on a number of blades, the blades are like this. So there we have taken the flat blades are there. These are the flat and vertical blades are there. Even one more things also we have discussed. Here one thing you can remember, all these blades or the buckets will be fixed on a runner with a equal distance. Okay, equal distance it will maintain on the runner. And this also we have discussed. This is in the middle of this part will be there, that is shaft. Here also the same thing will be there. The shaft will be at the middle of the point, and the shaft will be connected to the generator to generate the power. So this one also we have seen in the previous lecture. Even one more also we have discussed, like the blades, the curved blades are fixed on a wheel. The wheel will be like this, and the blades are fixed on this. It is like that. So the impact of jets will be on the side of this. side of this bucket. So the same thing here it is given, but here the impact of jets on the middle of this blade. But here previously we have seen at the end, at the corner, at the, you can say at one end of the blade, we can say. That's why the velocity triangle for this condition was, it was like this. Okay, this is the impact of jet v1, and this one makes an angle of alpha. This is our relative velocity vr1, makes an angle of theta. Okay, and this is the value of e1, the blade velocity, and this is total, here it is vw1, wheel velocity, and this is vf1, this is flow velocity. These things exactly we have already drawn in a previous topic, already have discussed, and outlet velocity also will be come like this. Okay, same thing will be there, or only angles will be different and the velocity flow also will be different. But in this condition actually you can see the impact of jets is on the middle of the blade. That's why here the inlet velocity triangle will be different, but outlet velocity triangle will be same what we have discussed previously. Okay, that's what I want to say. So first of all, let me find out what is the net head acting on the Pelton wheel. So we know that the H equal to net head acting on the wheel, acting on Pelton turbine, or we can say on the wheel, acting on Pelton wheel. So what is the formula to calculate the net head? We have seen during our discussion of head of turbines. There I have told you that head of turbines is nothing but, or net head of turbine will be calculated by the gross head minus the head loss during the flow. See, gross head is nothing but a total head. See, the impact of jets on the blade. So obviously from a dam, the water used to come from the dam. So suppose this is the dam height. So how much distance or how much height is present from this tail race to the head race? That is called gross head. And the loss of head in the sense, and one more thing, gross head is to be considered when the turbine is not working, or when the dam is not open, we can say. That means the fluid is in normal condition, static condition. Okay, and the head loss, the loss of head will be identified when the water started flowing through the pipe. Okay, when it is moving condition. There's obviously we know that when the fluid is flowing through a pipe, there is some chances of head loss or loss of energy is there. That is called major loss due to the friction. And so here the same thing we already seen previously, and here we used to call HF. HF will how to identify, and this net head will be calculated, this total head and minus how much loss of head happened between this due to this flow. So HF will be calculated like 4FLV square by 2dg. This was the formula what we have seen previously. D star, actually you can write capital D also. So here L equal to the length of the pipe, V is the velocity of jet, and D is the, here D star we can consider the diameter of the penstock. Here D star can be considered, this is diameter of penstock, because the water is flowing through the penstock. So penstock is nothing but a pipe only, this one. This penstock, or due to the long pipe, it is called the penstock. So this is about the net head acting on the Pelton wheel or Pelton turbine. Now, as I told you, we need to draw the inlet velocity triangle. So first we'll go for the inlet velocity triangle. Inlet velocity triangle. And one more thing, some other parameters are there. Just before going to this, let me tell you. So one is V equal to the velocity of jet. The same velocity of jet will be converted into different terminology, like V1, that will be the inlet velocity, or we can say the absolute velocity of the jet at inlet condition. So this velocity V1 actually it is to calculate that the inlet condition by the formula of 2gh. Okay, by the formula of 2gh. H equal to, as I told you, that net head. So that I told you that H equal to net head acting on the Pelton wheel, and this V1 will be calculated by this formula, and this will be useful when you solve the problem. And this is about the velocity of jet at inlet conditions. Similarly, velocity of jet, as I told you, this one. Here you can see this is the velocity of jet. Like here initially how the velocity of jet used to strike on the blade. And similarly, u is the nothing but the velocity of the plate. Okay, this is, you can say, this is velocity of plate. And the velocity of plate is nothing but like after striking, the plate started moving continuously. Okay, so here same thing, like u equal to, we can consider u1 and u2. u1 is nothing but the velocity of plate at inlet condition, velocity of plate at the outlet condition. And how to derive, how to calculate this one? With the formula of pi d n by 60. So see, this plate or blades are fixed on the runner. So blade started rotating in the sense the runner started rotating here. Okay, because all are fixed. And this rotation, this speed will be calculated by this formula pi d n by 60. So n is nothing but here, this is speed of the wheel, we can say, or speed of the runner. So here also you can write this is speed of runner or speed of wheel also we can say. So these are the terminologies are useful for to calculate the net head, and this is gross head is there, loss of head, and this is the velocity of jet in the inlet condition, the formula, and this is the velocity of plate at this inlet condition, and outlet condition also can calculate. Okay, now we'll see the inlet velocity triangle. As I told you that there will be no triangle at the inlet condition because see here at the previously what I told you, that impact of jets at the one point at the plate, it makes an inclination to the direction of plate. Okay, how much inclination? That is alpha. But at this condition, if you see, it strikes at the middle. So here the alpha value is 0, alpha angle is 0. Similarly, the theta is nothing but the angle between the relative velocity and the direction of plate. So theta angle also, this is 0 degree. So what about this other terminology? We can see V1 is nothing but, we can write now here V1, if I can write it in terms of VW1, I can write V1 equal to VW1 cos alpha, velocity component in the horizontal direction. But here this theta is there, that is 0. So you can write V1 equal to VW1 for this condition. Now you can see the same VW1 was taken here because of, if it is inclined one, I have written there V1 equal to cos alpha is there, and that is VW1 cos alpha, that is 0 degree. So you can write V1 equal to VW1. This is one terminology. Similarly, now next we can write this is V1 VR1. Yeah, VR1 equal to what? VR1 is nothing but relative velocity of the jet. So relative velocity when is to calculate? When there is two movement are there in the fluid. Here it is jet is moving, another one is the plate is moving. So jet movement is V1 and plate movement is U1. So VR1 is the relative velocity of the jet, we can say, with respect to the plate. So we can write this is V1 minus U1, or else we can calculate, we can write V1 minus U. Both are same. So these are the terminologies what we got in this inlet velocity. Okay, now we'll go for the outlet velocity triangle. If you see the outlet velocity triangle, this is also simple. You can see our previous video lecture. Already I have detailedly explained there during the impact of jets, as I told you, for this condition and for this condition already we have discussed previously. Even normally impact of jets for a curved plate when it is moving condition also, we can see that video also. There also similar thing is there. Just I'll give a reminder of this, that when the jet of fluid is coming out at the outlet condition, this is the V2, which makes an angle of, at the inlet condition it makes an angle of what? Alpha. You can see alpha. But at the outlet condition it will makes an angle of beta here. It makes an angle of beta here. Similarly, the relative velocity which makes an angle of, at the inlet condition, this is theta. At the outlet condition that will make phi. Okay, this is the relative velocity. Now, so this is our Vf2, the direction will be like this, and this is V2, direction is like this, and here the V1, and what is the component of V1? Here we got VW1 cos alpha. So similarly here also we can write this is V2 equal to, we can write this one component of this V2. VW2 is the component of, we can say V2. Okay, and similarly this one also we can say the component of VR2. Anyway, I'll write to find out some notations. Let me find out. Velocity triangle at the outlet condition, we can write this is VR2 equal to VR1. Relative velocity in inlet condition equal to relative velocity to the outlet condition. And VW1 not VW2. VW2 what I can write, this one. VW2 what I can write here, the total one is nothing but I can write this is VR2, this one, relative velocity component, horizontal component, VR2. This is that component we can write at the outlet condition component, we can write CO, or else we can write this is cos phi also, it can be written here. This is cos phi, the total one, the total of this cos phi, this one. Okay, and what I have written here, VW2, that means this much distance, how much, this direction is this one, and this U2 direction will be this one. U2 will be because of U equal to what, velocity of plate, because we know that the velocity of plate is moving at this direction. Always keep in mind, after striking this one, the velocity of plate will be moving in this direction. But here if you see this VW2 wheel velocity will be in the reverse direction. So VW2 equal to what I told you, VW2 equal to find out this velocity, the total velocity or total distance of this, you can say total value of this minus this one. So I can write this is VR2 cos phi minus U2. This one we can write, or else we can write this is nothing but VW2, that is nothing but here VW2 also I can say the component of V2. Okay, VW2 equal to, we can say also component of V2. This is one thing. Okay, and VF2 also component of V2. Which component? This is vertical component of V2, and this is horizontal component of V2. Okay, I hope you understand. Now similarly VR2 already have written here, and the same thing I can write this is in terms of VR2. If I want to write like VR2 cos phi equal to VW2 plus this one also I can write VR2 cos phi equal to, we can write this is U2 plus VW2. That's it. So because you can see both are moving in the other directions. U2 is moving in this direction, VW2 is moving in this direction. Anyway, this is one term. Now what is our intention? We need to find out the force exerted by the jet. We need to find out the force exerted by the jet of water, in the direction of motion, This actually we have already found previously, like in our impact of jets, as I told you, for this one already we have identified there like how to calculate this. Anyway, again I'll tell you how to calculate this one actually, what the formula for this. To calculate the force exerted by the jet on the direction of motion, so actually the formula is, we know that F equal to Fx equal to mass flow rate. This is flow rate into initial velocity minus final velocity. So what is the mass flow rate? or we can say this one actually came from F equal to, we know that, mass into acceleration. And the same thing we can write, mass into acceleration equal to, we can write a change in velocity with respect to change in time. So this mass with respect to change in time, again, not this one, let me write, okay, this part I'll write in place of mass, I can write rho into volume, because we know that rho equal to mass by volume. So mass equal to rho into volume, I can write this volume by time. This is second. So volume per second, and this is dV is there. Now this one we can write rho into Q, and this is change in velocity dV. Now again this one I can write in place of discharge. This is Q, discharge, meter cube per second. So the same unit is meter cube per second, this one. So this one I can write rho AV into change in velocity, initial velocity minus final velocity, we can write this one. The same thing we have written here, mass flow rate, initial velocity minus final velocity. So mass flow rate, we can write again, this is rho A V1, and this is initial velocity minus final velocity. Now here, this mass flow rate, we need to consider only V1, impact of jets only, okay? And we cannot consider the relative velocity here. For other terminology, we can consider the relative velocity, but when we see the mass flow rate of the fluid, we will only consider the impact, that what is the flow is there, what is the mass flow rate of this fluid is there, that only. Because we know that relative velocity is to consider, but when it will be considered, when only one plate will be considered, that means the plate is fixed or plate is moving only for that condition. But here you can see one plate is moving, another plate is coming, that plate is moving, another plate is coming. So plate continuously movement is there, and impact of jets will be there on the plates. So while taking the mass flow rate, we need to consider only V1, not VR1, keep in mind. And what is the initial velocity? Initial velocity, we need to consider VR1, because the velocity, the relative velocity at inlet condition, that we need to consider. Okay, so here we can write, this is rho A V1, and this is initial velocity. You can write this is VR1 minus VR2 at the outlet condition. So yeah, now we can write Fx equal to, we can write this is rho A V1, okay, rho A V1, and VR1, what I have written, VR1, that means the relative velocity at inlet condition. So that is V1 minus U. So we can write, yeah, V1 equal to, we can write VW1 also. Let me write VW1 minus U, VR1. Let me tell you, let me show you here. You see V11 equal to V1 minus U. So V1 equal to VW1 already I have written here. So I can write VW1 minus U. So same thing I have written, VW1 minus U. U or U1 you also you can write, no issue. Minus VR2. So VR2 equal to what? VR2 also we can write, this is U2. Here we can write U2 or U only you can write, because I already told you that U1, U2, U3, sorry, U equal to, okay, here I can mention it. Here already mentioned here. This is velocity of plate, U equal to E1 and U2 also. Both are same, because the only single plate it is moving. So that is velocity of plate. Okay. So here also let me write on place of VR2. In place of VR2, what we got here? Yeah, VR2 equal to VR1. Then after that, we got this is VR2 cos phi equal to this one, U2 plus VW2. So VR2 cos phi, why I have written here actually, because we need to consider the direction of motion, the velocity in the direction of motion of the plate, in the direction, in this direction. So we cannot consider only VR2, we need to consider VR2 cos phi. Okay, that how much we got? U2 plus VW2. U2 plus VW2. So U2 plus VW2. Okay, and this one, yeah, U2 plus VW2. Now actually this is minus of minus this one, it will come. Okay, because if you see the direction is in this direction, reverse direction. Okay, so we need to consider this is VR2 minus of this one, because this is coming reverse direction and the plate is moving in this direction. So what exactly, I'll tell you, minus of this term. So minus of this term in the sense this will be minus, and U2, yeah, this is actually U2 minus VW2 actually. This is U2 minus VW2, and minus of minus will be then plus will be there. Okay, let me write here one more terminology. Let me write here Fx equal to rho A V1. This is VW1 minus U, and this is minus, this one you can write, this is minus U2 minus VW2. Okay, now I just can write this is rho A V1 and this is VW1 minus U, and here minus of, this is minus U2 and this is plus VW2. Now if you write here, yeah, now this term, this is now you got the same thing. Okay, so here we can write this is rho A V1 bracket start, this is VW1, this one I can write U or U1, whatever you want, right, minus minus plus U2 you can write, or U equal, you can also write, this is minus of minus plus, this is VW2, and finally this will be cancelled and we will get rho A V1, and this is bracket start VW1 plus VW2. Okay, this is our force exerted. This one we can give an equation suppose, and this already we have derived previously during the impact of jets. That's why I want to tell you this already we have derived. Okay, now at this condition, if you see what is the angle of this beta, the angle of beta is always 90 degree here. Angle of beta is 90 degree here. So the beta is the acute angle here. So you can write here beta is acute angle. Acute angle in the sense this is less than 90 degree. Beta is less than 90 degree. So in this case, the vane or the mass of fluid, okay, strikes that vane will be rho A V1. As I told you, rho A V1, not relative velocity VR1. Okay, and here A equal to, we know that impact that area of jet. This is area of jet, and how to calculate this one also we know that that is pi by 4 d square. So now we need to find out, as a final one, we need to find out the work done. Once you calculate the force, then we can go for the work done. Work done by the jet. Work done by the jet on the runner. On the runner per second. Okay, on the runner per second. So we know that the work done equal to, we can calculate how to calculate the work done. Actually only work done means we can calculate the force into the distance covered. Okay, force into distance. Now work done by the jet on the runner per second, in the sense, now what we can write, force in the x direction into distance with respect to per second. This is time. So distance per time, we know that velocity. So we can write Fx into velocity. Velocity of what? Velocity of the runner. So we can write velocity of runner or velocity of plate, we can say. So Fx already we got here. This is rho A V1. This is U, yeah, this is VW1 plus VW2 into U, and the unit will be like Newton meter per second. This one we can give another one equation. This is for work done. Okay, this is for work done by the jet on the runner per second. This one also we have already calculated previously. If you see the previous one, there the same equation is there. Now once you calculate the work done, Then very simple to write the power also. Now same thing we can write here, the power given to the runner, power given to the runner by the jet, is nothing but just with respect to this work done, just to divide into 1000 and kilowatt will be there. That is nothing but rho a v1, and here bracket start vw1 plus vw2 bracket close into u divided by 1000. So this is nothing but our final output, we can say, and this is, we can write kilowatt. So this is about the power, and this is about work done, and this is about the force. So I hope you understand this derivations. Slightly lengthy, but already things are done previously, and the outlet condition is no need to do understand again if you have seen previous video. And only thing you need to understand the inlet velocity diagram. Remaining all are very simple. I hope you understand. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.